I'm extraordinarly grateful that the other people that are not morning people, and I'm definitely not a morning people, are here at this ungodly hour. I had thought about what to talk about today, and I realized it's going to be 8 a.m. or something like that. So talking about details of science just didn't seem right. And the other thing that I thought is that I got a little sentimental. It's now about 15 years since I started working on networks. And I realized that, wow, maybe a good bunch of the people in the audience were teenagers when I started working on networks. So, you know, maybe it will be interesting to reminisce a little bit about what was going on and some of the work being done. So I'll try to give a very, very personal view of things. Because I know I will be crunched for time and I don't want to rush at the end with the thank yous, I'm going to be talking about work that was primarily done by these three people here to whom I'm extraordinarily grateful. And also, I mean, I have other collaborators, but the collaborators that are listed here were the key people in some of the work that I'm going to be talking about. And it has been truly a pleasure to interact with all of them and learn from all of them. And of course, there is funding. We cannot do anything without it. So let me just start by asking a question. How many of the people in here would call themselves physicists? Come on, I know it's early in the morning, but try to put your arms higher up. Okay. Not bad. Actually, not as many as I thought. How many call themselves statistical physicists? Yeah, not bad, not bad. How many love power laws? I should add, how many have love-hate relationships with power laws? So I said I was going to give an history of things. And, you know, there is the very ancient history with Euler's work, you know, Moreno's work on sociograms. And I'm having this in here because a bunch of you are physicists and may not remember everything. Of course, we all know about Erdős-Rényi and random graphs and the kinds of analysis that they did. We know about the experiments in the 60s by Stanley Milgrams. We know about theoretical sociology and the work of Harrison White, looking at social roles, structural equivalence, and all of that stuff. We know about the wonderful work of Lynn Freeman on centrality measures and of Ron Burton on structural holes. But for most of us, things sort of started out about 15 years ago. And I like to tell stories, and today the theme is going to be Westerns. And maybe I should have brought a cowboy hat. I don't own one. But, and the last 15 years have had a little bit of schism to them. So I'm saying 15 years, but we all know that, you know, the paper that started it all, from my perspective, was Watson-Strogatz paper on small world networks. And this was extraordinarily exciting. I remember reading this paper and kind of almost jumping and thinking, this is so cool. And the point is that, I mean, it was so cool and there were a lot of people ready to jump on it. And one of the reasons why they were ready to jump on it was that because networks were sort of in the air. And I had been thinking about networks from another perspective. And there was this paper that we put in the archive. Actually, at this point, we had wasted a few months with Nature and Science. But what we were thinking about was extinctions. Why do you have mass extinctions? And the way that we were thinking about it was in terms of a system in which you have essentially a network of species that interact. And I think what was interesting about this case is that the model that we made for how the species interact was neither a lattice nor sort of a random graph. It was something in which we imagined that there were layers and there were connections across layers. So there was kind of an interesting structure in there. Now, we end up publishing this paper in PRL in '99, but I think that having worked on this project was something that really was making me ready to want to work on networks. And being ready, one of the things that we looked is we jumped on the work of Watson and Strogatz right away and tried to figure out what else can we learn about it. How prevalent are small world networks? And as some of you may know, we made a mistake in that paper. We got an exponent wrong. And what I also want to highlight is that we came out and acknowledged that we were wrong. And I want to say this because one of the things that sometimes is worrisome about what's going on in networks sometimes is a difficulty in acknowledging when something is wrong. And I think the goal of us when we are doing sciences is try to get the best possible understanding of what actually goes on. And I know I'm sounding like a cranky old man, and I'm getting to be an old man, and I'm cranky, and it's early in the morning. But I think this is a very important point. Science is a collective endeavor in which we are trying to learn about nature and about reality. And we all make mistakes, and it's important when you make a mistake to be able to, be a grown-up about it and recognize it. And so sometimes it's sad that you read things in the literature in which people are repeating the same mistake when there has been a correction, an acknowledgement that something was not the way that it was said to be or thought to be. The excitement didn't stop, and they were coming fast. And the resolution in here is terrible, but otherwise you'd be able to see the dates. So there was the incredibly exciting paper by Rebecca Albert and Jeong and Laszlo about the diameter of the World Wide Web. And then the even more exciting paper in October '99 about the emergence of scale-free networks. And I want to repeat this because it's scale-free networks is exciting. We all love power laws. But at some point, I think we have fallen into a trap of thinking that everything is scale-free. And that is not true. And for those of you that know this movie, it's a very cool movie in which James Stewart plays a guy that is a senator. And he comes back to a town. He was elected as a senator because he's thought to have killed a bad guy that was terrorizing a city. And he's coming back, and he's talking to a reporter, and he decided to come clean. And he's telling that actually the John Wayne character was the one that killed the bad guy. But the reporter looks at him and says, when the legend becomes fact, print the legend. And I think sometimes with scale-free, we are getting a little bit into a situation in which we are printing the legend instead of thinking about what is really going on. So what is going on is that not, as we showed in 2000, is that not everything is scale-free. And this is the issue of having to, not just take your bias, but look at the data seriously and try to understand what's going on. In here, we can see some of the evidence for things being power law. And the resolution is really terrible, but the point is that this was for collaborations between actors, the web, and the power grid. And this is a power law feed to the power grid. This is an exponential feed to the data on the power grid. And this is an exponential feed to the data now on a log-log plot. And it's obvious to anyone that the power grid is not scale-free. It's sad when you see papers that still say that it is. In fact, there are many cases that are not power law. The distribution of collaborations of actors, and this was a projection of the graph onto the set of actors as a very small power law regime. Friendships are actually Gaussian. So C. elegans, a neuronal system, is also not power law. It's exponential. So sometimes I think people in the outside think that everything about network science is about power laws and scale freeze. And that's not what it is. Now, going back to the story, the excitement with all of these things led to an explosive growth in research. And I call that explosive growth a little bit the good, the bad, and the ugly. And the reason for that is that I think there was some really outstanding research being done, and outstanding research in areas in which the motto that Laszlo Barabasi developed, think networks, was particularly crucial. About let's look at these systems and let's look at them in terms of networks, because that is going to enable us to advance. And I think there were outstanding advances. And studying food webs, I mean, it's hard not to talk about the groundbreaking work of Neo Martinez and his way to look at food webs. And later, I think a lot of us caught up to it and actually have moved this field forward. The study of epidemics has been, I believe, another tremendous success in which people like Alessandro Vispignani, Robert May, Mark Newman, Dirk Brockman have made tremendous advances. And I think this is a fascinating area in which they are pushing us to a situation in which we'll have the equivalent of predicting the weather, in which we'll have a way to predict how epidemics are developing and progressing at the level of countries, at the level of continents, at the level of the entire world. Another area in which I think there's been a huge amount of progress and understanding, and not only understanding, but understanding with insights on which we can act, has been in the study of scientific collaborations or collaborations in general. I think some of the work, and I'll talk a little bit more about this later, some of this work can be actually seen as a strong scientific support for scientific collaboration, for people communicating across disciplines. And it's something for which some of us had gut feelings about, and some of us had made kind of jumps and say, this is a good thing. But I think that this work has actually revealed that there is a hard quantitative justification and support for that idea. There has also been extraordinary work in the area of synchronization, community detection, looking at the structure of energy landscapes. With all of this work, one of the things that I found that was really exciting and brilliant, and there are lots of names that will be missing in here, but is that we are taking the thinking about networks to new directions and to directions that are important and relevant, that actually can change what we do. And I think this is the exciting aspect to what Brian was saying, for instance, bringing economists into the fold and using the thoughts, the ideas and concepts that we have learned about networks into these areas to actually affect, in an important way, new fields. There were some things that were not so good. And I have to confess that the initial stage about network research was somewhat disappointing. It was like everybody had their favorite hammer, and there was the nail of complex networks, and so people just banged away with, percolations on small world, scale-free. I mean, let's think about sustainability, right? I mean, do we really need to kill another tree to publish a paper about Ising model on a small world or scale-free network? I said I was a cranky old man. And then there was the thing that drove me crazy. And I could start banging my head on this iron right now. If I have to edit or review another paper about another scale-free model, I'm going to kill the author, okay? You will receive an envelope with anthrax. No, that is too slow. I know I sound like a cranky old man, but I'm actually an optimist person. And even though I can't resist complaining about stuff, network science has reaffirmed my belief in science. The idea that you can get people from around the world looking at the problem together and trying to make real progress and advancing our knowledge. And I think there are examples besides those ones that I talked before in which we have accomplished that. We have looked at important problems and we have tried to solve them together as a community, and we have made significant and lasting impact. And this is an history. In 2006, I proposed to the organizing committee of the APS March meeting an invited session on networks, and specifically about uncovering the structure of complex networks. You guys might not have noticed, but by 2006, there were very few papers about community detection. Actually, we had a paper rejected by PRL because the reviewer thought that community detection was an unimportant problem that didn't matter. So I organized this session, and at that time, I gave a little introduction in there, and I said that, I said the same crap that I just said about small world and scale free. And I said, look, I think what we need to look about is how do we uncover the structure of networks? Because if we have a network that is not all homogeneous, but has groups and subgroups, global properties like what's the average path length or what is the degree distribution tell us nothing about the network, about how it got created, how it evolved. If we have a network that has groups and the groups grow and aggregate, then that can tell us something about how that network evolved and why it evolved and all of those things. So I was saying this is an important thing, an important problem to look at. And I think that this was a problem in which we have made tremendous progress. And, and there were big challenges. And like what many computer scientists thought, when you don't know how many groups there are supposed to be in your network, this is not a trivial problem at all. But we were able to solve it. And there has been a tremendous amount of progress. And I think one of the reasons why this has happened is that many people working in this area took very serious the point that we need to have standards. We have to have a way to check that what we are finding is correct or not. And, and we have to compare different algorithms. We cannot have everybody publish a paper and saying, I have a new method, and now we have 500 methods for detecting communities, right? If you are proposing a new one, there better be an explanation. Does it improve what we can do? Does it solve some area? And I think these great studies that by this group in Tarragona and Barcelona really set the stage by looking and comparing the performance of different methods and by defining a benchmark, a set of networks that you know the structure and you can see, is my algorithm able to find that structure or not? And cranky old man again. The Zachary Club is not a benchmark. The Dolphins are not a benchmark. And the Santa Fe Institute Collaboration Network is not a benchmark. Okay? These are 3 ridiculously small networks about which we cannot possibly, for sure, know what the structure is. Okay? This other benchmark in which you can set groups, you can set ratios of inside to outside links is a benchmark. And so we need benchmarks. We need ways in which we can validate our algorithms and we can determine performance values. Okay? Otherwise, we are not doing science. This is another benchmark that we need to do. And we need to verify things like, you know, if I repeat the algorithm 1,000 times, do I find the same partitions or not? You know. Now, as I said, community detection is a very important problem. It can tell us something about how a network is organized, which can tell us about how it evolved, how it grew, what functions the groups may be formed, and ultimately may also give us a way to represent networks in a way that is actually graspable. A lot of network representation is it's a hairball, right? Your cat just spit that off. We don't get much insight by looking at something like that. Community detection starts to give us a way to actually look at large networks in a way that is actually understandable. You can use the module representation to summarize information about networks. And what we suggested is that an analogy to maps would be fruitful. Because just like in a map, when you change the scale, the information that you are displaying gets altered and actually enables you to grasp where things fit within the big picture and the medium picture and the small picture. By having a modular representation of a system, you can do the same thing, especially if you can also find a way to represent which components, individual components of the network are important. And so that's what we proposed in here. We proposed a definition of roles of nodes in networks that are based on the topology of those nodes. And our argument is that, yes, while quantity of connections is an important indicator, is not the only one. There could be other measures, especially if you have a network with communities, that could be equally important. So if you look at this toy network and you start to looking at the nodes, it's clear that, you know, A and B are sort of similar in the way that they are organized and connected within the network, right? They have both lots of connections. So it's clear that they should have sort of their role. There is also clear that there are all these other nodes that are peripheral. You know, they have very few connections inside their group, and so it's clear that they should have some kind of separate role. But what I think is interesting too is that once you have communities, there is another thing that becomes possible, which is connecting the different groups. So you can have nodes with few connections that actually enable connections between groups, and that gives you a possibility of having different roles that are also important. And so we proposed this And, you know, like any proposal that is a jump, it starts with complete hand waving, right? I'm waving my hands. I wasn't before, but now I am. And you can buy it or not buy it. But the point is, can we test these? And what we did is we looked at metabolic networks, and we defined these roles in different metabolic networks for different organisms. And we asked the question if there is any relationship between conservation across organisms and roles. And if you have a two-dimensional diagram in which you can classify your nodes, and you say, well, I have quantity in here, I have quality in here, I would expect things out here that are high in quantity and quality to be important, so to be highly conserved. And that's what you find. These things here are very highly conserved. If you have things in here that are low in both aspects, you expect them not to be that well conserved. And that's what you find. These R1 nodes, peripheral nodes, are not highly conserved. It's factor of 3 in the conservation. So it makes sense. Now, my intuition was going no way in this across the other direction. I was not sure what would be more important, have lots of connections or connecting modules. What is interesting is that this is having lots of connections inside of your module, and this is having few connections that connect modules. And these ones are more highly conserved than those ones. So interestingly, at least in terms of metabolic networks, being a connector of modules is more important and more crucial than having lots of connections inside your module. Another aspect that we discussed about was, can we find a hierarchical structure, right? If you are trying to make a map that has representations at different scales, you need to be able to identify those scales. Now, this is a network of the air transportation system. So each circle in here represents an airport, and you'll have to believe me that there are lines connecting those circles, and that means that there is a direct connection between those two airports. Now, if you look at this network, this is a hairball. You know, there is no insight about structure in here. But we know that there is structure, right? There are continents, there are countries, there are restrictions about how many airports outside of your country you can land in. So we expect that there is a structure with different levels. And we defined a benchmark in which we knew what the structure was. But besides that, because no benchmark can capture the complexity of real networks, we chose to look also at the air transportation network. And what we were able to show for our algorithm is that, okay, you'll have to believe me in here. Okay, there are some lines in here that are supposed to be gray, but they are yellow. And this is the coast of Africa in here. This is the Arabic Peninsula. This is India. And what we did is that we found this organization of the network at the highest level, right? Each color in here represents a different module. And then we went to one of those modules, we actually did them for all, of course, and found the submodules and then the submodules. And what is interesting in here, for instance, is that there are those little circles in here in the Caribbean that are the same color as South America. It may seem odd until you realize that that is Cuba. And then it makes sense that Cuba is actually not part of the same module as the United States, okay? If you look at the organization of this large group that is sort of what we call the old world, and you go down some layers, at some point you find out that the groups actually are contained within borders. So this brown color here is India. That's Bangladesh. That's Sri Lanka. That's Arabia, Saudi Arabia. So, you know, it's a way in which we actually can verify if our results make sense or not. And this is the point, validation, right? If we are contributing to the advance of the field, we cannot just produce another algorithm and test it on the Zachary Character Club. Okay? Right now, there are 200 algorithms. We need to test them against the other ones, and we need to demonstrate that they work. Now, however, I have 0 minutes. You are lying to me. Okay.
Going negative now.
8:59. I'm going negative. Food webs. This was great. Actually, those power law fits were not so great. An exponential fit works much better. But what works even better is actually being able to make a theory that actually can make sense of these things. And Neo developed a beautiful, beautiful model. And when I read this paper, I was jumping about as high as when I read the Watson-Strogatz paper. And when Roger came to work with me in Boston, you know, that's the thing I wanted to work with him. And, you know, you start with a model, you start with a collection of data. And I mean, Jennifer Dunn has been amazing with trying to get these data accessible to people. We need data that we are all working on. We need models, and we need to try to look and find an understanding. And what we're able to do is find an understanding of all these diverse food webs in which simulations, theory, and data were agreeing surprisingly and extraordinarily well. Impact of team assembly. These are collaborations between scientists. This is what the data that we look at. And several of us spend time scraping data from Web of Science by hand to get data on 30,000 teams and thousands of papers, okay? Why? Well, because then you can find out information about decreasing repeat of collaborations leads to publication in higher impact journals. So actually, when you bring new collaborators in, you get better outcomes. And this was, again, a very nice interplay between theory and experiments. Brian had been working on a model. You know that I started way late. Brian had been working on a model about assembly of teams. And with data and simulations, we were able to make sense of it and actually find a real insight that can guide the way in which we understand the world. I think the future of network science is addressing problems that matter. And I would recommend the poster by Julia and the talk by Adam, in which we are looking at some problems that I think matter, and we are bringing a network view of things to gain insight about these systems. So I apologize for all the crankiness, and I thank you very, very much for your patience at 8 a.m.